In this chapter, we're going to be studying statistics. In this lesson, we're going to look at bivariate analysis.
Okay, hi everybody. So now we're going to talk about something called bivariate analysis. So bivariate, two variable. Okay. So we're looking for the relationship between pairs of variables x and y in a data set, and we usually use like a scatter plot or a scatter diagram to represent that. The relationship between the two variables as expressed in some sort of a scenario or event where they're both pertinent, and we plot them to see how one influences another here. So the relationship between the x and the y here is going to be their correlation with each other, okay? And we use that correlation so that we can make predictions, okay? And the stronger the correlation, the more confident we are in our prediction. So we're going to talk about how you can judge the strength of a correlation, and there are there's general ways of doing it, and there's more specific kind of algebraic ways of doing it. But ultimately, because of the amount of data here, we're going to end up using the calculator to do a lot of that work for us. So we draw a scatter diagram. You just plot the points, quite honestly, on the variable here. You've just got to remember that your independent variable is going to be down here, and your dependent variable is going to be up here on the y-axis, okay? Or if you really want to kind of nerd out about this, we call the x-axis here our abscissa, and the y-axis our ordinate, just to sound fancy. Now, let's talk about the relationship a little bit here. If you can see that the general trend of the data is to increase as you go to the left here, in other words, it's got a positive slope, okay, then it's a positive correlation. On the other hand, if you can see clearly that it's going to have a negative slope to it, then it's got a negative correlation. I mean, that's kind of maybe not the best word to use there when I say slope here, because it doesn't necessarily have to be linear, but it's either going to be positive going up or negative going down. That's the idea. However, if there is really no distinct pattern to it, like here, I can draw a line of best fit through these guys here, and it's relatively clear what that line would be here. There's like no line. I have no idea what to draw here. So we said that the correlation is close to 0. Okay, this is going to have a positive value for the correlation. This will have a negative value for the correlation. And we're going to see in a little bit here that the closer that the value is to 1 for the correlation, the cleaner it is, the easier it is to see the relationship here. So 0 is kind of that tipping balance where there's no real visible correlation there. Okay, so now let us take a quick look at the strength of the correlation. So we just talked about the direction, now we're going to talk about the strength. So in a strong correlation, we see that the data really closely approximates a straight line. In other words, I can draw a line through that with a lot of confidence that I am expressing the relationship fairly clearly. In a moderate correlation, okay, you can still see the relationship in the data, but it's maybe not quite as obvious. There's a little bit more spread in the data. When there's a strong correlation, there's not a lot of spread in the data away from the line of best fit, okay, the general trend. Here there's a little bit more spread in the data. So we can still be fairly confident with our line of best fit, but we're not as confident. And then in a weak correlation, there's only a vague connection here. In fact, you might not even be confident that you can see a line of best fit in there. That's a weak correlation. Okay. If you're not at all sure what the relationship is supposed to be or intended to be, that's probably a weak correlation in the data. So, what else can we say? Well, data can be linear. It can be nonlinear. And basically what we're looking at here is if it's linear, it's got a constant slope. And if it's not linear, I mean, the defining feature is it's got a variable slope. Okay. In other words, if I try to draw tangent lines to this, whatever, it's just the slope keeps changing. Okay. If I pick 2 points, find the slope, it's different if I choose another 2 points there. Okay. And now correlation does not necessarily imply causation, and this is probably, it's not necessarily something that's going to get tested on in this particular course here. But if you're going to take something away from this might impact you in the real world, so to speak, this is kind of it here. Just because there's a correlation between two data values or two sets of data here doesn't imply causation. Okay, so the example that I give here is you might notice that as your shoe size increases, one's vocabulary also increases. Okay, so as your foot gets larger, your vocabulary gets larger. So does that mean that the size of your foot, okay, determines the size of your vocabulary? And the answer to that is no. No. As you grow, your vocabulary gets larger. Okay, it's not dependent on your shoe size. It just happens to happen at the same time as one's foot gets larger. Okay, so there is this confounding factor here, age. The older you are, okay, the larger your shoe size is typically because you're growing, and the larger vocabulary is because your brain is also growing and learning. Anyway, now let's take a look at some examples. Okay, so for this question here, this example, we're being asked to represent the following data in a scatter plot. Okay, so we've got our X down here and our Y here, and actually, I see no reason why we wouldn't go up by ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you frequently have to make just a decision about how you're going to represent your data and about the scale you're going to use here. So here's my point here. I've got 1, 1, 2, 3. Now, oddly enough, you'd be surprised how many times people flip the X and the Y coordinates. So please pay attention to that. 3, 3, 4, 5, 4, 6, 6, 7, 6, 5, 6, 6, 7, 8, and then 8, 9. Okay, so there's our scatter plot there. Now, is the relationship linear or nonlinear? Well, I have really no clear indication that this is not linear. I mean, it looks fairly linear to me. Okay, we're not trying to confuse you when we do this. We're not trying to trick you and say, aha, look, if you look at the outside points, there's no trick going on here. If it just looks roughly linear, then it's linear here. I mean, this up here, this one is clearly not linear if you follow the trend of the points there. But this one, yeah, it's going to be linear. Describe the strength of the relation here. Okay, well, this is going to be, I mean, there's a relatively clear line of best fit here. So I would say this is going to be moderate to strong. Okay, now there may be a little bit of disagreement on this, and so be it. That's fine. That's fine. But I think we can all agree that this isn't weak. I mean, there is a relatively clear relationship that's being implied by that data. So moderate to strong. Now we want to talk about the line of best fit, okay, which is also called a regression line. Okay, so when you see that expression used, the regression line, that's all they're talking about is the line of best fit. Okay, so don't get thrown off by that. And it just basically shows the trend and direction of the data in the scatter plot. And then we use that to make predictions. And so, as you can probably guess at this point, the stronger the correlation in the data, the easier it is to not only make that line of best fit, but then to trust the predictions that you're making are going to be accurate. Now, typically, when we start drawing a line of best fit, we're gonna do it by eyeing it, right? You pull out your ruler, you're gonna kind of try to draw it so it's the middle of the data. You're gonna try to draw it with kind of roughly the same number of points above the line as you draw below the line. And so one way of doing that to help yourself out there is to choose a point that you're going to draw the line through, and you might use the mean point. Now what the mean point is you're going to find the average or the mean value of the independent variable and the mean of the dependent variable, and use that to come up with a point, okay, that you'll then kind of pivot your line of best fit around. So let's take a look at an example of what that might look like. Okay, so let's take a look at this example here. It says consider the relationship between fat content and calories in some common restaurant foods. Okay, so we've got a whole bunch of those there, and here's your fat, and here's your calories. And so we're going to find the mean number. Okay, we're going to find the mean point, and then we're going to construct a line of best fit. But first of all, let's make a scatter plot here. And so we're going to put fat in grams, and then we'll put calories over here. And then for our fat in grams, what should we go up by here? Let's say we got to go up to, what's the large value here? Looks like 34, 10, 15, 20, 25, 30, 35. Yeah, so we go up by 5s here. So 5, 10, 15, 20, 30, 35, 40. That should be good. Now, going up here, I think what I got to do here is I'm going to have to break the graph. So little line right there, just to show that I'm going to jump up here. We're going to start at 200. And then 300, 400, 500, and 600. So now I'm going to plot my points here, my data values. So up here, okay, and I'm just going to follow along the points right here. So for those of you that have the data here, it'll be easy to follow along. But it's going to be 9 and then 260, so it's going to be somewhere about here. 13, so we'll be kind of in the middle there. 320, so a little under there. 21, we're going up to 420, a little bit over. So I got kind of a nice little linear pattern going on here. 30 is going to be 530, so it's going to be somewhere around there. 31, so just slightly over there is going to be 560, so it's going to be a little bit over. 31, okay, 550, so it's going to be right on that line there. 34, 590, so just underneath. 25, 25, going back up here to 500. 28, just shy there, it'll be up at 560. Whoops, 28, 560, so a little bit over. 20, 440, so just underneath there, and then 5 up to 300. Okay, so there's our data values there. Now what we're going to do is we're going to come up with the mean points. So I'm going to go back up to my data here. I'm going to find the mean for each of these here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, of course it's 11. So pull out the calculator here, and we're going to add those all up. So 9 plus 13 plus 21 plus 30 plus 31 plus 31 plus 34 plus 25 plus 28 plus 20 plus 5 divided by 11. Okay, and so down here I'm going to get 22.5, although I mean I'm not going to be able to really graph that 0.5 little bit there, so 22.5. On the other hand here, we've got 260 plus 320 plus 420 plus 530 plus 560 plus 550 plus 590, keep going here, 500 plus 560 plus 440 plus 300, oops, divided by 11. And I'm getting 457.3. Okay, so now I'm going to plot that point right there on my grid. So 22 or 23, comma 457. Okay, so 23, let's say, so roughly about there, and then 457, so just slightly over there. So it's going to be like right there. So again, that's not one of the points in my data, but that's my mean point. Okay, so maybe we put this over here, we'll put our mean point, and that was going to be 20, let's round that, 23, comma 457. And now what I'm going to do is I'm going to draw, okay, my line of best fit. I'm going to try to get equal number of points on either side here. So what do I got here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, that's, that's basically it. That's roughly it. So something like that. Now, is that the best line of best fit? Yeah, Probably not. You know, and if other people were to do the same thing, basically with the same work here, you'll probably find that our slopes will be a little bit different here, which is why mathematicians have developed kind of some standardized versions or approaches that we use, and the calculator is programmed with those, and we'll take a look at some of those in a bit. Okay, so in this question, we've got Mr. Rossel's 10 student scores out of 100 for their classwork and their final exams are shown below here. So we're going to say Dean was absent for the final. Okay, so absent. So we're not going to include his grades in the final in finding the mean point. But what we're going to do is we're going to find the mean point of the classwork and the mean point of the final exam score. We're going to make a scatter plot. We're going to draw the line of best fit, and then we're going to come up with the equation and use that to estimate Dean's mark on the final. So this is kind of the full meal deal here with what we're doing. We're going to plot the data, get the regression line, and then use it to make a prediction. Okay, so we're going to put classwork. Okay, and we're going to assume that that's the independent variable because it affects the final mark. Now I got to break my graphs here, and I've already kind of gone through and looked at how that should work here. I'm just going to double check that my numbers are going to work out right here. So I want this to be, I think, 50, 60, 70, 80, 90, yeah. So 50, 60, 70, 80, 90. And then here, I actually think I want this to be my 50, 60, 70, 80, 90. Yeah. So this will be my 50, 60, 70, 80, 90. I think that works out kind of best for what I want to see here. So now I'm just going to go through and take a look at plot the data points here. So I've got 95, 95 when I look at the data here. And I'm just grabbing it from up here. So I'll just kind of change this so you can just see here. I'll zoom out just a little bit here. Whoops. So you can see both of those. So we got 95, 95. So there's Ed. 66, 59. So it's going to be like right here. 88 will be like here. 85. So right on the line. 75. And 77, so about right there. 90 and 92, 90 and 92, so about right there. 82 and 70, okay, so 70 is right there, so 82 about right there. Okay, 50, 50 right here, and 40. Now 40, based on what I've got here, would be right about there. And then 45, 50. Okay, 45 would be right there, 50 here. I don't know why I made that point as big as I did. Remember, we're not going to use Dean here. And then what do we got here? Jeremy's got 84 and 80. Whoops, 84 would be right about there. Okay, so now what I want to do is I want to come up with the mean point. So what we're going to do here is we're going to come up with the mean for both of these, but remember we're excluding Dean there. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that will be 95 plus 66 plus 88 plus 75 plus 90 plus 82 plus 50 plus 45, skipping Dean, plus 84, divide by 9. Okay. And so we're getting 75 for the average or the mean of the class marks. Now I'll do the same thing for the final mark, 95 plus 59 plus 85 plus 77 plus 92 plus 70 plus 40 plus 50. We're skipping over Dean, and then divided by 9. And so our average there was 65. So now that's the mean point that we want to plot. So 75, comma 65. So that's the point right here. Oops, have I got that right? Yeah, right there. Okay. So now I want to draw this. So try to get as much as I can the same number of points above and below. So I've got 1, 2, 3. I got 9 other points there. So I'm going to try to draw this. And that is going to be tough. Did I do that? Did I get that right? I'm just going to double check that I have the right number of values there. 2, 3. Yeah, I do. Okay. So seems a little bit low for that, but that's okay. So what have we got here? 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So let's try this right here. Now, you can tell right now that I'm going to be off kilter a little bit because these points here are kind of way out of whack with these things. I've got 1, 2, 3, 4. That point is on the line 1, 2, 3, 4 above the line, but that idea of just keeping things above and below doesn't really match up here. But if I tried to keep this, I mean, I could have also done it. Well, actually, there's really no other way that I would have done that. Would have kept the same number on both sides. But that's okay. That's okay. So now we're going to come up with the equation of this line. So I know that it goes through the point 75, 65. Now I'm going to pick another point that's on the line. And actually, it looks like I got a really nice clean one right here at 80, 75. Okay, so now I'll find the slope. So 75 minus 65 over 80 minus 75. Okay, well 75 minus 65 is going to be 10. 80 minus 75 will be 5. And so I got a slope of 2. Actually, that's kind of a nice value here. So now if I put that into my equation of a line here, that'll be 2x plus the y-intercept. And now I'll just pick one of those 2 points, and it doesn't really matter which one. So let's pick 75, 65. So 65 is equal 2 times 75 plus b. And that's going to be 65 minus 2 times 75. Just do this on my calculator really quick so I don't get that wrong. So negative 85 is equal to b. That's the y-intercept. So therefore, y is equal to 2x minus 85. So what that suggests here is if you get nothing, if you get 0 on your classwork, you'll get negative 85 on your final exam. Now, does that make sense? Yeah, not really. But this is just a model that should be relatively accurate within the kind of the area that we're working here. So now, to figure out what Dean should be getting here, his mark will be 2 times 80 minus 85. So 2 times 80 is going to be 160 minus 85 will equal 75. So we think Dean should be getting 75% on his final exam. Okay, so for this question, the question says, a study was done to investigate the relationship between the age, x, in years. So let's make sure we write that down so we have everything in mind here. So we're going to let x be the age, okay, in years. And the time, y, time, this is in minutes. Which child could run 1 kilometer? To run 1 kilometer. Okay, so now I know what my variables are. Data from children between ages 7 and 18 was collected, and the equation for the regression line was found to be, okay, so here's our regression. Y is equal to, you know what, I don't particularly like the way that's written. I'm just going to write it so that it's in the form that I'm more comfortable with. So we're going to interpret the slope and the y-intercept. Okay, so here's my slope right here. Slope is negative 1/2. Now, this is going to be negative 1/2. And think about how the slope works here. The slope is the ratio of the rise, the change in the rise over the change in the run. So this is going to be the units, this is going to correspond to the units vertically to horizontally. So this will be time to run 1 kilometer. So this is going to be minutes per year. Okay? And so basically what this means, okay, is that we are going to, what does this mean? We're going to, well, look at it like this. We're going to lose 1 minute for every 2 years the child advances. Basically means the older you get, the slower you get. Which which is not that far out there. Yeah, I mean, you can train and whatnot and get better at that, but yeah, there we go. So we're going to lose a minute for every 2 years that the child ages between 7 and 18. Now, the y-intercept here is 20. So this means, okay, when the child is born, okay, so you're 0 years old, okay, so I'm going to put a little thing here, x is equal to 0. You can run the kilometer in 20 minutes. Okay, and so our response to that should be, what? But that's okay. Okay, that's okay. That simply means that there is that the regression equation that we've got here, or the actual relationship here, is probably not linear. It's probably close to being linear between 7 and 18. But in general, this is not a linear relationship. And so you really can't make predictions too far beyond the data, right? You can't always extrapolate from the model that you create, because your model might not be taking into account all of the different factors that influence that relationship. Okay, so yeah, sometimes you get these weird sort of predictions here. Okay, in this problem, we read that a biologist wants to study the relationship between the number of trees, x. Okay, so x is the number of trees per hectare, and the number of birds, y per hectare. Okay, so the number of birds per hectare. Okay. She calculates the equation of the regression line to be, okay, that. And we're supposed to state, and I'm going to write this in a form that I like. I'm going to change the order there. State the gradient and the y-intercept and what they interpret them. Okay, so first of all, gradient is basically just the same thing as the slope, just another way of saying it. And we've got 5.4, and I can rewrite that as 5.4 over 1, because it helps me make more sense of the slope here. The units on the vertical axis is going to be number of birds. So this is going to be 5.4 birds per tree. Okay, and so that's the relationship that we get here. Okay, basically what you're looking at here is on the whole, you're going to get 5.4 birds for every tree in that hectare. The y-intercept, 8, sorry, and I should have used a different symbol for that. I should have used the B. Okay, the B, I should have said equal to. The B is equal to 8 here, and basically what this means is we get 8 birds even if there are no trees. Okay, and that's what that would imply, that relationship. Okay, so now we're going to take just a moment here, kind of regroup here, then we'll do some more examples. First of all, we're going to define the gradient. Is the amount the y increases when x increases by 1. So just a moment ago in an example here, I mentioned that gradient and slope are basically the same thing here. And what we might say here is, the way we're defining it here, it's more like a unit slope. Okay, so we'll just make that a little bit more precise here. So that's what we're looking for. Now, let's take a look through this here. It says if we only found the regression lines by eyeing it, everybody's going to get different lines. And I'd mentioned this earlier here. So it would be better if we had a different method that worked to find the line of best fit and gave us a standard result. That way, when we're all working together on this, we're all getting the same thing, and we can agree on the model and its predictive value here. So, and there are lots of different ways that we can do this. So that being said, what we want to do here is we want to choose a method and then kind of have people agree that that's the method that we're going to use in any kind of given problem here. So your calculator has a few in there. One of the ones that we're going to look at here is now called the least squares method of finding a regression line. Okay, and what that does is it picks the line through the data and it's got your data points here kind of scattered all on either side here. And what it does is it measures the distance that each data point is above or below the line and minimizes that sum of those. Now it squares the distances so that it gets rid of the negatives there, but it minimizes that sum all the way across there and chooses that line. So once the values of the independent variable are entered into list 1 in your calculator and the dependent variables are in list 2, we're going to use linreg on our calculator. And I'll show you where to find that. We're going to take a look at some examples right now. Okay, so in this question we read that the table shows the distance in kilometers and airfares from Changi Airport, Singapore to 12 destinations. Use your graphic display calculator to sketch the scatter plot with the line of best fit, write the equation of the line of best fit, and use it to estimate the cost of a 1,000-kilometer flight. Okay, so a lot going on here. First of all, we're going to go to the calculator and we're going to enter this in. Okay, and I think we can agree that the fare is going to depend on the distance. So I'm going to press stat, okay, remember stat, and we're going to press enter on edit. And in list 1, I'll enter all the distances. So 576. 370, 612, 1216, 409, 1502, 946, 998, 189, 787, 210, and 737. Okay? And I can see that it's waiting for me to enter the 13th data value in, so I know that I've entered 12 in there. And that's important, just to make sure that I'm doing this consistently. So now 178, 138, 94, 278, 158, 258, 198, 188, 90, lots of 8s here. 179, 138, and then 98. And good. And my two lists are the same length. Okay, that's important. You'll get a dimension error if they're not. Okay. Now, first thing that I want to do here is I'm going to quit out of here. Let's graph it. Okay. Let's sketch what this looks like. So to do that, I'm going to press second and y equals here to get into my stat plot. I want to press enter to go into the first stat plot here. I'm going to turn it on. And already I kind of like what's going on here. It's highlighted the first graph here. That is put this up closer here. That is my scatter plot. We'll take a look at some of the rest of these ones later here, but there's my scatter plot. The X list is list 1, the Y list is list 2. It doesn't really matter what marks I use or what color it is. I don't really care. But now what I'm going to do here is I'm going to, instead of pressing enter and just letting it graph it, because the calculator will just use whatever default window settings are there, I'm going to press zoom. And I'm going to go down to zoom stat, which is number 9 here. So what the calculator will do is now look at my lists and pick window settings. Okay. Oh, now what that means, there they go. Okay, what that means is I got to go just for a second here. I'm going to wait till it stops thinking. I'm going to go in there and I'm going to get rid of the graphs that I had sitting in there. Let's try that again. Okay, so there's my little axes there. There's my points there, all scattered about. Okay, now I want to create this line of best fit, so I'm going to quit. To get the line of best fit, we're going to press Stat, and we're going to go over to Calc, and then I'm going to go down to the linreg, that's number 4. Okay, that's linear regression, AX plus B. I'm going to choose that. So now the calculator is waiting to know where my lists are here. Okay, so X list, Y list, store regression equation. Yep. But I wanted to get rid of the frequency list here. I'm not dealing with a frequency list. This is a kind of an X and a Y set of data here. Calculate, and now there's my regression equation. Okay, now I would like to see my regression equation. And there are a couple of ways that you can do this, quite honestly, but I like doing this one here. So I'm going to go back to y equals y1, and I want to put the regression equation right here. Now if I go sorry, I got rid of it. So I'll go back to this. You could have written down the values for A and B and then typed out the equation here. But your calculator keeps everything in variables until you write over them. And I really want you to get familiar with this. So I want you to press the VARS button here. We're going to go down to statistics. And the third menu over is EQ. That's equation here. And the very first option you get is regression equation. So we just did a regression. It's storing that regression equation here. And so when I press enter, it puts that equation right there. I don't have to write that out, memorize it. And now if I press graph, there's the line of best fit, okay, drawn out for me. And that is what we call the least squares method of the line of best fit. The least squares, on that last question that I did in this this video here, where I had the marks, the least squares would have probably been a better a better line of best fit than what I had done. So here we go. So now what we want to do is we want to write the equation of the line of best fit. So I'm going to go back to that. And what did I have here? I should have probably written this out when the calculator first gave it to me here. So it'll be 0. Let's just say 1. Well, we'll go to the nearest thousandth here. 117x plus, and then I have to go over and get the y-intercept there. And I'll do the same thing. 83.267, whatever. Okay, there's my value there. And so now I want to figure out the cost of a trip that's $1,000. So let's go back to the graph here. So if I go second trace to get into the calc menu and I press value, it's waiting for me to enter the X value. So I'll enter in 1,000. And then it tells me that that cost would be $200.64. So a 1,000 kilometer flight would be $200.64. Yeah, got that right. Okay, there you go. Okay, now we're going to measure the correlation. So earlier on, we had classified it as weak, moderate, or strong. Now we're actually going to give a number to it. Okay, so just like in the previous question here, where we stopped eyeballing the data to get a line of best fit, we let the calculator use a program to get it. Now we're not just going to look at the data and kind of give it a rough idea of what the correlation is. We've got a value here. And we're going to use a correlation coefficient developed by Carl Peterson. Okay. Oh, I said Peterson. I meant Pearson. Sorry about that. Carl Pearson. So here we go. The Pearson product moment correlation coefficient. Hey, whoa, that's a name. So it's denoted by R, little r here, and it's the value. It's going to be a value in the interval -1 to 1. Okay. So it's always going to be some value from -1 to 1, and it measures the correlation between the two variables x and y. So it's really a strength. It's a measure of the strength of the linear dependence on two variables. So how closely they approximate a straight line here. So when you take a look at these things right here, just to give you a sense of how it works here. Okay, let's zoom in on this a bit. This has got an R value of +1. Because that is, they're all on a straight line. And it's got a positive slope. That's why it's a +1. So positive slope 1, because that's 100% on a predictable line here. This one here, positive, because it's got a positive slope, but it's a little bit more scattered, okay? So this is like your moderate correlation at 0.7. Ugh. Now, this one's starting to get pretty weak. This is quite scattered here. It's still got a sort of a positive slope to it, which is why it's still positive, but at 0.3, it's really all over the place. Very hard to trust a prediction made with data that has an R value of 0.3. Now, -1 simply means it's got a negative slope. That's not its slope. It's not a slope of -1. It could have been negative and have a much different negative slope. The 1 means it's all on a line. The negative simply means it's got a negative slope. So here, same sort of thing. It's still pretty clear what the line is, but it's a little bit of scattering here. Still, it's negative because the slope is negative. And then here, -0.3. Again, as you go to the right, it's still kind of going down, but it's very weak. Now here, this is what just weak period looks like. There's no relationship here. I can't draw a line to it. I can't tell if that's positive or negative. It's just kind of all over the place here. Okay, so now, which way? This way. Oops, back. So now we're going to get the graphic display calculator to give us the correlation coefficient, because it's got it in its little brain there to be able to do this for us. And so what we have to do is we have to turn the diagnostic on feature from your calculator's menu. And I'll show you how to do that in just a moment here. And once it's turned on, okay, it's going to display the Pearson correlation coefficient with the when you're doing the appropriate regression there. So just to give you an idea of what you should be looking for here, if it's between 0 and 0.25, that's quite weak. If it's between 0.25, basically you're splitting this up into quarters here, right? In the first quarter here, that's really weak. Second quarter, that's still pretty weak, okay? But 0.5 to 0.75 is moderate. And if it's over 75, that's usually pretty strong, okay? You can fairly clearly tell what the line is that you're getting from that. Okay, so anyway, I'm going to show you how to turn the diagnostic on, and we're going to run through a couple of examples. Okay, so now, whoops, wrong way. So Jenny wants to determine if there's a correlation, if there's a correlation and what the strength is between the number of spoons of plant food she adds and the number of additional orchids that grow from the plant. Okay, so here's our data here. And we've already indicated that this is going to be X and this is going to be Y here. And so what we want to do here is just figure out how strong the correlation is. And let me show you how to do that. So to start off with, I want to turn on the diagnostic here. So I think the easiest way to do this is to go second, catalog. There's probably another way of doing this, but this is easy here. And then I'm going to press X to the -1. And the reason I'm going to do that is it's the D. Just above it is the D. The calculator right now is waiting for an alpha code there, a letter. So if I press this right here, it takes me to the D's. And now I just got to drop down a little bit. And diagnostic on is not too far down. It's right here. So I press enter to choose diagnostic on, and then press enter to activate it. That's all I got to do. It's on. Even if I clear this right now, it's on. Okay? So now we're going to enter the data in. So stat, edit, and I've got data in there already from a previous question, so I'm going to get rid of that. So I go up to the name, press clear, and enter. Up to the name, press clear, and enter. And now let's enter the data in. And so we've got 1, 2, 3, 4, 2, 3, 8, 7. Okay, so there's our data. And now what I'm going to do, I'm going to quit out of there, go back to this screen. I want to do find a line of best fit. I want to do a regression here. So stat, over to calc, and we're going to come down to the linear regression, AX plus B, enter. So list 1, list 2, this is not a frequency chart, so I don't have that. Yeah, it can do that. I want it to calculate the regression. And now notice that it's giving me an R of 0.877. Okay, now don't worry about the R squared right now. You can talk about that later. Just the little r here is 0.877. So R is equal to 0.877. This is a strong correlation. Okay, there's a very strong relationship between the number of spoons of plant food and the number of orchids that you'll get as a result. Okay, so that's how you would do that. Now, don't worry about turning off your diagnostic. It's really not doing anything to the calculator other than telling the calculator to take this extra step there. If you clear your calculator, it will reset that to diagnostic off. So prior to an exam, for example, or when you go in to write an exam, you might have to turn that back on to make it work. Okay, everybody, one more thing before we go here, just a couple of notes. So when you use a line of best fit to analyze the relationship between two bits of data there, That line of best fit should work really well when you're trying to interpolate or find data values in between known data values. But extrapolation that's problematic, okay? Our assumptions about the data being linear, or actually whatever type of graph we assume it is, whether it's quadratic or cubic or whatever, it doesn't really matter. Your assumptions about that might be incorrect beyond the data that you're given. And we've already seen like an example like that in this video already. So you have to pay attention to that. Extrapolation might not be trustworthy here. And it's also worth pointing out that when we're finding values using a regression equation, that the correlation coefficient impacts the level to which we can trust our solution. So with a question up here, if we were to make a prediction based on this, well, we might have a fair bit of faith about it because the correlation seems to be quite strong. But the weaker that is, the less faith we can have in that, or in any prediction that we make based on that regression line.